This is, let's say, the terminology you have heard in many places, that molecular structure. So first of all, we would like to know what exactly do we mean by molecular structure. Okay. So there are two aspects of molecular structure. One is the geometrical structure. And other one is electronic structure. So together they will constitute what we know as the molecular structure. Now, in order to have two different aspects here, like the geometrical structure and the electronic structure, first of all, you can see that we are talking about geometry separating the electronic component, and electrons are also coming without bothering about the geometry. So this particular aspect, we can do it within what we call Born-Oppenheimer approximation. So we will come back to this approximation, but before that let me tell you what do we mean by geometrical structure and what do we mean by electronic structure. Now suppose if you have a molecule, let us say water molecule, you have the oxygen, so this is oxygen, hydrogen, hydrogen, this is, let us say, water molecule, and you know that there is something called equilibrium bond length, equilibrium bond angle, and this is what we call the equilibrium geometry or equilibrium molecular structure. So here you can see these are the nuclear positions. You don't bother about electrons, where the electrons are. So whenever we talk about this geometry, for which you talk about molecular point group, symmetry, like this is a C2B symmetry. In order to have the C2B symmetry, you must have this particular arrangement, okay? But you could have had it in number of ways. It is not that some rod is fixing these two, so they are all moving objects, okay? So when they are placed in that particular configuration, actually there is no force acting on the system, or the potential energy is minimal. That's why we will call that this is the stable geometry. There may be many unstable geometries also. But the first thing what I should tell, that in a molecule, how do you see, how do you visualize a molecule? There are several nuclei which are positively charged, there are several electrons which are negatively charged, and they are moving. So they have their own kinetic energy. There is electron-nuclear attraction, nuclear-nuclear repulsion, electron-electron repulsion. So under the mutual Coulomb field, like the resultant of all those repulsive and attractive forces, they will try to arrange in such a way that there is no force acting on the system. In addition, they have their kinetic energy. So that sort of dynamical setup of a set of charged particles, some positively charged and some negatively charged particles, is your molecule. And atoms are special types of molecules, so you have only one nucleus. Okay. So in this case, when you get that situation, that during their movement, they are going to a situation where all positive forces and all negative forces, they will balance each other, okay, all attractive and repulsive forces, so that the potential energy is minimum and the force is zero on each nuclei. So most of the time the molecules will try to go back to that particular situation. That is what we will call the equilibrium geometry. Because why equilibrium? Because there no force acting on the system. So that is from the classical mechanics. When there is no force on a system, we call the system is in its equilibrium. That's why we call this equilibrium. And the corresponding bond lengths, bond angles are called equilibrium bond lengths and bond angles. Like here, this is your equilibrium bond length, this is your equilibrium bond length, and this one is your equilibrium bond angle. Okay, and these are the bond lengths. So this structure we'll call the geometrical structure. Okay, so this is one part of the story. What happens to the electrons? We are not bothering about the electrons at this moment. So what happens to the electrons? The electrons, they will arrange in such a way, again, that they will also get a corresponding, say, stable electronic configuration. Now, when we know the electrons are distributed over here, how do you represent in quantum mechanics? That if you know the coordinates of the electrons, you can define a function, the wave function or electronic wave function, that will tell you how the electrons are distributed over space. Or precisely, if you go for psi star psi, that will tell you the corresponding probability density, and that will tell you in space how the electrons are distributed. Like these are the places where you have maximum probability, etc., etc. So you have a specific arrangement of the electrons for the specific geometrical structure, and that arrangement will tell you what we know as the electronic structure. That means when we say molecular electronic structure calculation, what exactly do we mean? That we have to calculate the electronic wave function, that's it. That will tell you how the electrons are distributed over space.
So just one question. Do we consider that we know the Morse code and the recipient theory, or is high?
Nothing. We know nothing. Because now we are within the hardcore quantum mechanics. We are applying only Born-Oppenheimer approximation we are going to apply. Okay? No approximation. VSAPR, etc., they are all models, and in many cases they fail. So now what we are doing, in order to do that, as I told you that electrons and nuclei, they are moving together inside the molecule, and when they are moving, they have their own kinetic energy and they have their mutual Coulomb attraction, repulsion, etc. How can you take away the nuclei from the electrons? Because they together form the set which we call molecule. How can you tell one without the other? So what we have done, we have considered this as a separate entity, the electronic structure as another separate entity. So two great scientists, Max Born and Robert Oppenheimer, they postulated, and they had shown mathematically also, that, and in many cases it is valid. Let's say about 95% cases it is valid. But there are 5% cases like where you have Jahn-Teller effect and other types of electronic excitation, etc., for different systems. You may not get that approximation to be valid. And accordingly you get what we call adiabatic approximation and all non-adiabatic cases. So in this case, what is happening? Electrons are moving, nuclei are also moving, but you think that any nucleus is about 2000 times heavier than the electron. So the motion of the nucleus is a bit sluggish, it's a slow motion. Electrons are having fast motion. So by the time any nucleus is moving, electrons must have moved several times here and there. So when one electron moves from one place to the other, which we call electronic transition, okay, because here you have some electron distribution. When it moves, you have another electron distribution. That means you are having different wave function now. So that electron movement, when it takes, it sees almost a static nucleus. Because when it is moving so slowly and during its movement, it is seeing it is as if, say, it is fixed. Okay, it's frozen. So we can now, considering a frozen nuclear framework or static nuclear framework, we can solve the electronic motion through some electronic Schrodinger equation. Then when you look into, there are two different time scales you can see. So when you look into that time scale where nuclei are making the movements, by that time electrons must have moved several times. So nuclei will see the electrons as a smeared out charge distribution over a very large area, because by that time it has gone here, there, etc. But it will see an averaged out charge distribution. So we can calculate the behavior or the movement of the nuclei when they are interacting with that charge distribution. Okay. So we have separated out electronic motion from the nuclear motion. Okay. So now we will see mathematically how do you do it. So we will start from the actual Schrodinger equation, time independent Schrodinger equation of a molecule. Okay. So you have, so there are two sets of variables. I am writing with the vector, means you know that R1, R2, R3 up to whatever. Similarly, capital R. So these are for the electrons, these are for the nuclei. Okay, because the positions are specified in terms of their coordinates. Okay, so electronic coordinates, and the electronic wave function is a function of electronic coordinates. Okay. So your total wave function will be a function of these two sets of variables. Your Hamiltonian also, and this would be your E . As there is no time, I am writing small psi. Okay. For time dependent case, I write the capital psi. So this is the total Schrodinger equation, considering electrons and nuclei per se. So no approximation yet. Now we will see, what do I say, that you can separate out now electronic motion from the nuclear motion according to Born-Oppenheimer approximation. So if you can do it within Born-Oppenheimer approximation, your H you can see the physics is written in that mathematical form. The total Hamiltonian composed of electronic and nuclear coordinates. I can write this as the electronic Hamiltonian and nuclear Hamiltonian. Nuclear Hamiltonian, actually they depend only on the nuclear coordinates, because you have to put in the Hamiltonian nuclear, electron nuclear attraction part, that's why electronic motion should be considered, but that electrons are smeared out, so they don't have any coordinates. So it would be only dependent on nuclear coordinates. But on the other hand, here, for a given frozen nuclear framework, you have specific nuclei that will determine electron nuclear attraction again, that will come in this electronic Hamiltonian. So you have some dependence, but this is not, as they are not moving, but they will have a fixed position. I am writing it with a semicolon, not with a comma. So that means this is a functional dependence, this is a parametric dependence. Okay. So let me explain what exactly do we mean by functional dependence and parametric dependence. Suppose if I write fx as e to the power lambda x, then x is a variable, lambda is a parameter. Okay. So similarly here capital R would be a parameter for the electronic motion, and lambda is like here, and x is say like small r, it is a variable of the electronic motion. What about the electronic wave function? And you know that energy is additive, but this is the probability function, it is multiplicative. So psi electronic R into psi nuclear R. Okay. So what are the steps? First we should see for the molecular structure calculation, and that is what we call quantum chemistry. So majority of that part is the molecular structure calculation constitutes that. Okay. So what exactly do we mean by this molecular structure calculation? That means both geometrical structure as well as electronic structure. So first let's see electronic structure. If you have to calculate, what do? So these are the steps. Freeze the nuclei. Okay. Freeze the nuclei. Solve electronic Schrödinger equation. Get electronic energy. So electronic energy will have a dependence on R. For different nuclear arrangements, different solution you will get from the electronic Schrödinger equation. Get nuclear potential energy. Solve nuclear motion. Nuclear equation of motion. Once you solve the nuclear equation of motion, you get new set of R. Okay. Then you go back. So you basically construct the whole of the potential energy surface by following this process. Okay, so you start from any arbitrary one and then iteratively you do it. All possible nuclear configurations should be obtained, and there you will see some will be maxima, some will be minima, and accordingly you get reactant, transition state, etc. everything. So this is the basic process what we consider. So electronic Schrödinger equation So this is your electronic Schrodinger equation. So here you can see in the electronic Schrodinger equation, your capital R has some information. So you get that information from the freezing the nuclei, solve it, you get electronic energy and wave function, and then you follow. I will tell you as we go further what are the different steps we'll have to take. Okay, so I am giving you some exercise. So this is your equation 1, 2, 3, 4. First, you substitute 2 and 3, put it here in equation 1. And see what do you get. And remember, H electronic will operate on psi electronic and H nuclear will operate on psi nuclear. Okay? So you have to operate this on this. Okay? This is constant as far as this operator is concerned, and this is constant as far as this operator is concerned. Okay? Okay? Are you getting this? No? Don't copy it down. You don't understand. Because as I told you that for this operator this is constant, for this operator this is constant. Okay. So do all of you get this? Yes or no? But what is this one? Make use of 4 to get this. Okay. So now here you can see these are all products. Okay. Here also this part and this is product. This is all product. So I can cancel psi electronic from all sides. Okay. Is that clear? Here I cannot do because here operator is there. But after that, this is just product. Energy, electronic energy is just a number. Okay. So that means what do you get? Okay. Is it fine? But now you see the explicit forms. Your Hamiltonian So the total Hamiltonian kinetic energy of the electrons, it will depend only on the electronic coordinates. Electron-electron repulsion, that will depend only on the electronic coordinates. Electron-nuclear attraction, that will have a parametric dependence on nuclear coordinate and also functional dependence on electronic variables. Kinetic energy of the nuclei, that will have only dependence on R, then nuclear repulsion. So this part is my H electronic. And this part is my H nuclear. Is that clear? So we have separated out. This is the Born-Oppenheimer part I am doing, electronic Hamiltonian and nuclear Hamiltonian. Sometimes in some textbooks you can see this is constant. If I have a, say, fixed set of nuclear coordinates, I can apply just simply Coulomb's formula and I can find out what is this. So this number I can add it here also. Sometimes in the electronic Hamiltonian also you can see this number is added. But you can put it here also, no problem. Okay. So now, in this case then what you can see, this equation becomes T nuclear R plus V nuclear R plus E electronic R psi nuclear R, that is E psi nuclear R. Okay. Now you have two just numerical values, so these are not operators. Potential energy is not operator. So this one, if I identify this as some kind of potential energy, then you can see this is just a Schrodinger equation for the nuclear motion. You have the kinetic energy operator, you have the potential energy operator, you have the wave function. It is just the Schrodinger equation for the nuclear motion. Okay. So the concept of nuclear potential energy in quantum chemistry, or potential energy, we don't call nuclear potential energy also, we simply call potential energy. But now we know what exactly do we mean by the potential energy. Comes within the Born-Oppenheimer approximation, isn't it? So here, how potential energy is constructed? You freeze the nuclei, you get the nuclear coordinates in the frozen nuclear framework that you are doing to start with yourself, whatever your chosen, say, initial geometry, what you give, that gives you your, say, first capital R vector, and that is frozen. We calculate with that frozen framework, you calculate this electron nuclear attraction, solve the electronic Schrodinger equation, get the electronic energy. After you get the electronic energy, get nuclear potential energy. How to get nuclear potential energy? With that frozen nuclear framework, you can immediately calculate nuclear potential energy. Add this electronic energy, what you are getting, that is your nuclear potential energy. Okay. So you can see when you try to get the nuclear potential energy, the electronic energy is very important component that comes through the solution of the electronic Schrodinger equation. Okay. Then what happened? You have the nuclear Schrodinger equation, or Schrodinger equation for the nuclear motion at your disposal. The first thing what you can do, you can solve this equation. If you solve this equation from starting nuclear geometry, you get, say, other nuclear geometries or the corresponding probability, say, nuclear wave function. With that you can get the nuclear motions. Generally what we do is a kind of semi-classical approach. Electronic part is done quantum mechanically. Nuclear part is done classically. So because you know all the forces now, Coulomb forces, starting with your, let's say, initial geometry of the nuclear configuration, if you know the forces, nuclear repulsive forces and nuclear attractive nuclear forces, you can solve Newton's equation of motion to find out the new nuclear positions. Okay, in most cases, or you can solve Hamilton's equation of motion or Lagrange's equation of motion, any classical equation of motion to get new sets of nuclear coordinates. Once you get the new sets of nuclear coordinates, you freeze there, solve again electronic one. So you get now the potential energy for that new nuclear coordinates. Now if I plot my nuclear potential energy as a function of nuclear coordinates, so all possible nuclear coordinates I get over here, what I generate in general we call it a potential energy surface. Okay, that is the terminology you will hear here and there. So potential energy surface. Okay. If you get a simple diatomic molecule like hydrogen, you have only one variable because two hydrogen atoms are there, so you have only one bond length. So if you plot the potential energy, this potential energy as a function of the bond length, what you get is, perhaps you are talking about this. So this potential energy, big nuclear R, let's say for hydrogen atom as a function of nuclear coordinates, so I get it like this. Say for 1s sigma g, I get it like this, 1s sigma u star, I get it like this. So this is what is called potential energy curve, because here you have only one variable. If you have more variables, it would be, say, multidimensional stuff, and that you get potential energy surface or basically potential energy hypersurface. You have to take the projection on specific planes or specific surfaces. Okay. Now here you can see this is the point where the potential energy is minimum. So V is minimum means the force is negative gradient of the potential energy. Okay. So here force is 0 because it's a minimum. So force 0 means this one, here the force is 0. So this particular bond length we will call equilibrium bond length, because for this bond length the potential energy is 0. Do you follow? So whenever you hear in organic chemistry or inorganic chemistry, this is the equilibrium bond length of this molecule, that's the equilibrium bond angle of that molecule. Similarly, if you go for surfaces or hypersurfaces, your potential energy would be a function of several bond lengths, several say bond angles, torsional angles, dihedral angles, and ultimately you will get different types of maxima, minima, etc. Here you have only one minimum, you will get several of them. Okay, and in that case, you can, in principle, just scan the whole of the potential energy surface. You are asking something.
Sir, we are freezing the nuclear first step.
Be louder.
We are freezing the nuclear first step, right, sir? First step.
Which one?
First step here, we freezing the nuclear, and then at third step we are finding the nuclear potential energy. So for that we use nuclear interaction, and then we already solved the electronic energy, sir, and then we just sum it up. But when we consider nuclei as like it's frozen, its potential energy is 0, right?
Where?
At first step, sir.
Why potential energy is 0?
And we are freezing the nuclei. It's not moving anywhere. It's static.
It's not time dependent stuff to calculate the force. Force is derivative with respect to r, not with respect to time. Who cares whether they are frozen or something? Actually they are moving. We are taking time slices. That's it. Okay. In fact, let me tell you, you may have a confusion. So there are several states. So this is, let's say, for hydrogen molecule. There are several states, electronic states. This is 1s sigma j, 1s sigma u star. Okay, you must be knowing bonding orbital, sigma bonding orbital, anti-bonding orbital. Then you have 2s sigma, etc. Then p pi, etc., pi orbitals, etc. Okay. So all these orbitals, how do you get? Now here actually when I say this electronic Schrodinger equation, actually this is H psi n as En psi n. So these are your electronic. Okay. So when I solve at this stage, not only I get one, I get several. I get ground state. Here I have shown two. You get the whole hierarchy of states. When I solve this, how do I solve? That's a different matter. I can do Hartree-Fock theory, I can do DFT, I can do, in all cases I will get all sets of electronic energy levels. Okay. So actually, although I am plotting this in this continuous fashion, when you do the calculation actually for a given R, I get these are the energy values. Then for the same symmetry state, I connect them to generate this. But actual solution doesn't go this way. Actual solution at a given R, I fix the R. I solve electronic equation, I get H psi n El n. So 0, 1, 2, 3, all electronic energies are there, and along with the corresponding geometry you add, you get the potential energy. You plot it this way. Okay. So now you understood how the potential energy surface is generally generated. So here you can see that we told you that this is your say nuclear Schrodinger equation within Born-Oppenheimer approximation. Now as you can see that if you consider that Hamiltonian is additive, the corresponding wave function would be multiplicative. Okay. So now I can remove this part. What do you mean by now nuclear motion? So keep it at the background, let's digress. What exactly do you mean by nuclear motion? That means where the nuclear coordinates are changing. Okay. So first see, you have the molecule. Let's say this is your molecule. This is your center of mass and this is moving. Which motion do you call? What is the name of this motion? The whole molecule is moving. Translation. Okay, this is the translational motion. So when there is a translational motion, nuclear coordinates are changing. So this is the nuclear motion. So suppose now what is this motion? Vibration. So you have the stretching, asymmetric stretch, this is your bending mode. So the bond angles are changing, bond lengths are changing. This vibration is also a nuclear motion. This is what? Rotation also, you can see this is a nuclear motion. Now, suppose if we consider there is no interaction between translation, rotation and vibration, I can again consider the nuclear Hamiltonian now can be written approximately as the vibrational Hamiltonian plus electronic plus translational Hamiltonian plus rotational Hamiltonian, and the corresponding wave function as vibrational wave function into translational wave function into rotational wave function. If I put it over here, they will get separated out. So you will get completely separate individual degree of freedom vibrational motion. You solve it, you know that if you again approximate that it would be harmonic oscillator, you can solve it. You get orthogonal Hermite polynomials. You go for the rotational motion, you get associated Legendre polynomials. Okay, separately you can get, and ultimately you take their product, and whatever energies you are getting at them, you get the nuclear energy. There is yet another that you will not get maybe in many textbooks, but that is another one. Let me remove this. Suppose if you have a chemical reaction, okay, say A plus BC this is your transition state, this is your reactant, this is your product. Okay. I can define it this way. Let's say the nuclear coordinates or a capital R, say of A, B and C, if you say that the B and C coordinates are very close to each other and A coordinates are far off, that particular arrangement I will call that it is a reactant situation. When all the sets of coordinates are very close by, A, B, C, I will call it a transition state. You may have intermediates also, or maybe very, very complicated situation. When A and B coordinates are very close and C coordinates are far off, I will call it a product. So if I plot it, let's say I may get it like this. So I have reactant, product, say reactant, product, transition state 2, transition state 1, and this one another minimum, this we will call intermediate. So there are many people who get confused with the intermediate and the transition state. You can see along the potential energy surface, actually these are the projection along the minimum energy path. So transition state is a maximum, but intermediate is a minimum, like reactant and the product. Okay. So this is one dimensional. There may be several products are getting formed via several intermediates. So you may have branching in different ways also. But you can see that this is also a type of nuclear motion. I can treat them as the nuclear motion. And that's why if you want to study any reaction, even the reaction mechanism, you will have to follow the potential energy surface. Okay. So what is the general picture of a molecule considering whatever we have told? It has some equilibrium geometry where it wants to be there, around which it is executing translational motion, vibrational motion, rotational motion. So it is vibrating, but again coming back to its equilibrium, again vibrating, coming back, rotating again. Okay. So it's a dynamical setup. It's doing all these operations, nuclear motions also, but at the same time we have something at the background which you can call equilibrium geometry. But equilibrium geometry is not static because it is undergoing also vibration, translation, rotation, all these motions are going on. Okay. So that actually is the molecular picture, and they, in addition, they are interacting with other reactants, reagents, solvents. So that thing is going on. So you have to understand everything in proper perspective. I think I stop at this point. Next one, what's the time? most of us say there are two aspects. One is the geometry optimization, and another is if you know the geometry, let's say equilibrium geometry, you can straight away solve the electronic Schrodinger equation, get electronic wave function and calculate whatever property you would like. Now, solving that electronic Schrodinger equation for a many electron system itself is a very, very difficult task. And only for one electron problems you can solve them analytically. Like hydrogen atom, say all hydrogenic systems. Hydrogenic systems like hydrogen, helium plus, lithium 2 plus, etc. They are all one electron systems. Why? Because their potential, you don't have electron-electron repulsion, and their potential is central in nature. That means it depends only on the radial variable, not on the angular variables. Okay, this is just minus z by r. Okay, no theta phi. So it becomes very easy to solve them. And for one electron problem, the wave functions, in this case, let's say the electronic wave functions, they are called orbitals. Okay, so the orbitals are one electron wave functions. Okay, so like you know the orbitals 1s, 2s, 2p, 1, actually that is the way they come, 2p0, 2p minus 1, etc., etc. Then you take the linear combinations to get px, py, etc. These are all orbitals, that means one electron functions. Okay. Now suppose if you have a many electron system, then what happens? So I will introduce you to one, say, typical mistake what we do. Most of the chemists basically do. So in case of atoms, also in case of molecules. In case of atoms, they are called atomic orbitals. In case of molecules, they are called molecular orbitals. So there also you have to take a single electron molecule. Their wave functions are molecular orbitals. We have developed something called electronic configuration, and that you will see starting from very school level, you were taught this electronic configuration. So remember 1s2, 2s2, 2p6, 3s1, etc., etc. So you have learned what does it mean, and you have developed something called Aufbau principle. Okay. So you have different energy levels. Starting from the lowest energy, you apply Pauli's exclusion principle, Hund's rule, and then you feed the electrons in those energy levels. What actually you are doing, you have several electrons, they interact with each other, they repel each other, and that's a physical effect. So that means if I tell them that they belong to, let's say, orbitals, we consider them to be independent particles, as if electrons are not seeing each other. I am taking separate electrons, but it is not that all electron assembly. Say a many electron system is looked into in a single electron framework. Okay, it's not n electron system. These are n one electron systems. So you generally don't get the actual picture. and major interactions are missing in this whole episode. So you have to do something if you want to really know what type of behavior, particularly let's say the electronic aspects, you have to take care of this anomaly. So that we will develop in course of time. Okay. So we will talk about DFT in greater detail if time permits. But unless you have this background clear, I think you won't be able to appreciate that either. Okay. So now here you can see that for many electron atoms or even many electron molecules, what exactly do you do? So that means you have to resort to some approximate technique. So there are several approximate techniques. So two important techniques are perturbation technique, perturbation method, and another is variation method. Actually, most of the quantum chemistry packages we use variational method. Some places we use perturbation method also. So, but if you want to treat any molecule in presence of some external field, the perturbation technique becomes somewhat easier. So here will tell you something about this variation method and variational principle. So it is based on a principle that is called variational principle. And some of the items I am introducing you to you right now, but I will tell you the exact mathematical meaning in due course. Okay. So, what is variational principle? Suppose you have some function which maybe, let's say, in a general situation h psi I as, let's say, ei psi I, it may be the solution of the Schrodinger equation. But suppose I cannot solve this equation. So I say that I approximate this function as some known function xi plus a linear variation del xi. Okay, and this one we will call my trial wave function. Okay. Now this variational principle says that with this trial wave function, if I construct my energy, so it would be Hamiltonian remains same. So we know the expectation value over this trial function. We will call this as, so this is approximate energy, remember, because this is not wave function. We will call this as the energy functional. So this is the word, mathematical word I am introducing without telling the meaning, but this is called energy functional. And this is actually the core subject in density functional theory. Density functional theory. So you have to know what is the functional. So that I will come back later on, because there I have to tell you again some mathematics. Okay. It's not that running a code to solve chaos equations. No. You have to learn what is density, what is functional, what is theory, that you have to learn. So in this case, this energy functional, I can construct, and suppose if I give a variation, this is called linear variation. I have already told you linear operation. Linear variation, if you have a linear variation in the wave function, The variational principle says there is no linear variation in energy. This is actually the variational principle. When there is a linear variation in the wave function, there is no linear variation in the corresponding energy functional. That means energy functional will have a quadratic variance, and that is quite obvious because here variation, here variation, so you will have a quadratic variation. Now the question is, in calculus, when there is no linear variation, that means there is no first order differentiation, first order derivative is 0. Okay. What does it mean? Can you tell? If for a function, if the first order derivative is 0, what does it mean? What happened? It may be constant, it may be only constant. Just now you have seen, I have shown one first order derivative to be 0. Maximum, minimum, together what we call extremum, inflection point, constant. These are all the situations where the first order derivative is 0. So what it means now, that if the first order variation is 0, if you calculate the trial wave function and find out the energy functional and actual, remember you know the, say, consider that you know the, say, actual energy, which is the functional of the Hamiltonian over the exact wave function. What type of behavior, if you compare them, would you expect? So firstly, energy would be either a maximum or a minimum or constant or inflection point. That's why its first order variation is 0. So what is the nature of that? That we will see, and that tells you in the variation method. So you see, variational principle is this one. I am telling now variation method, which gives you a technique for, or approximate technique for the solution of the Schrodinger equation. But it is not Schrodinger equation, it is there in almost all branches of science, engineering also. You go to the operation research, you go to economics, everywhere people are doing optimization problem. This optimization comes from this principle. So what is that? So we'll try to understand. So here you have your solutions like this: E0, E1, E2, etc. And here you have psi 0, psi 1, psi 2, etc. Okay. These are your exact solutions. So it was first shown by Eckert. This is called Eckert's upper limit theorem. Actually, this is the crux of quantum chemistry. Any quantum chemical calculation, you have to follow this Eckert's upper limit theorem. Now, what is that Eckert's upper limit theorem? Say, he had applied a very clever trick. So suppose I write this okay. So what is the clever trick? He considered that this is Hamiltonian operator is a Hermitian operator. Its eigenfunctions will constitute a complete orthonormal basis set. That's the property of any Hermitian operator. Okay. So now I can expand this trial function as a linear combination of these functions. Don't bother whether we know it or not. If we know it, obviously we have solved the problem. But he considered, let's consider we know. We don't know, but we need it for some purpose. So he wrote it like this: sum over I, Ci, psi I, H, sum over J. I am writing it with two different indices because they are dummy indices. Basically, this is also C1 psi 1 plus C2 psi 2. This is also C1 psi 1 plus C2 psi 2. In order not to lose the cross terms, I am writing it in this fashion. Then you have sum over I Ci psi I, sum over I Cj psi j. Okay. Or it becomes sum over I, sum over j, Ci star Cj, then you have psi I H psi j, sum over I, sum over j, Ci star Cj, psi I psi j. Okay. And this one, psi I star psi j, this integral is your Hij, this matrix element, and this one is overlap matrix element Sij. Okay. Now we also know that this basis set is an orthonormal basis set. That means this quantity is nothing but your Kronecker delta Ij. Isn't it? Because it's an orthonormal basis. What about Hij? Can you tell? Any one of you? What should be the Hij? What is Hij? What? Huh? Hij is what? You see, Hij H psi j is Ej psi j. Ej you take it out. So only psi I will remain. Rest all terms will go because psi j will be 0 all, and this one would be 1. That means Hij would be Ej when I equal to j. Okay, and rest it would be 0. So that means here in this summation only one summation will be there when I equal to j. So this one would be sum over I Ci mod square Ei by sum over I Ci mod square. But this one also, as it is normalized, it is also 1. Okay. If you don't understand, ask me. Don't simply copy down. Okay. Don't copy it down. You tell, is it okay? Simply here H psi I have used the Schrodinger equation, then I get psi I psi j, all possible terms. When I not equal to j, it would be 0. When I equal to j, it would be 1. So only Ej terms will be remaining. And now, so you can see, and this would be Ci star Cj, Ci star Ci. Okay, because all cross terms will be 0 because they will be multiplied by zeros. Okay. Perfect. So from there, what you can see, your E xi is mod Ci square Ei. Okay. Perfect. So I can write this as, so suppose I subtract the ground state energy from both sides. This is my ground state energy. I have subtracted E0 from both sides. But E0 I can multiply this with sum over I Ci square, because this is mod square. So this is just 1. So I multiply with this. Okay. So this becomes sum over I Ci mod square Ei minus E0. Okay. Now here this one is quadratic, so it is positive. Sum of several terms, and Ei minus E0, only when it is E0 it becomes 0. In all other cases it is positive, because all other energy levels are above it. So it must be greater than equal to 0. Okay. Or okay. So this is actually your variational method comes from here. Now what is then the method? What it says, whatever may be your trial function, you choose whatever, calculate the energy functional, you know the technique how to calculate. That energy can never go below the exact ground state energy. Okay, period. So you got this. So you cannot go below the exact ground state energy. Then what? Then obviously that information is not giving you any, say, help in solving the Schrodinger equation for this. He had the job to bring in something unknown, and he had proven, considering the properties of Hermitian operator, etc. And but at the end of the day, we don't know what are those psi i's. So what will you do? You start with a trial function and there adopt a specific route to change the trial function, so that you see that energy value is decreasing. It depends on your energy, time, computer power. You keep on doing this, and wherever you are satisfied, you do it. That means I have hit the ground state energy. Do you understand? So that gives you the typical variational technique for electronic structure calculation. Do you have any question at this point before we go further? Tell. Do you have any confusion first of all? So what you can see that you have now developed a method for electronic structure calculation, but through some approximate method. We are not solving the differential equation per se. Only thing what we are bringing some trial wave function, constructing energy functional, and then we are optimizing that so that the minimum value. But you see, if you understand what is called calculus of variations, how you can vary a function, there you have to learn functionals and the typical functional analysis that will tell you how you can, in principle, optimize, not only minimize, to get to heat the transition states, you have to find out the other types of solutions also, the maximum solutions also. But the thing is, the method, if you learn, it becomes easier. It is not that numerically you calculate energy functional every time and compare that whether it is going down or going up. Okay, that when your computer is doing, you can check the number, how they are moving. But actually, you have to know the technique, how you can minimize a functional or so that is the theory of optimization research. You want to reduce the price of a commodity. You want to maximize the profit. Everywhere this is going on, all throughout the subjects in economics, epidemiology, everywhere. Okay. Or say production in an industry, how you can improve the product yield. That's also just operation research is going on. So I think, what's the time? So whether I can start another 11:40. Okay, so just slightly I will tell you, and then maybe in the next class. Actually, I am somehow going away from the schedule. That is the problem. But I think it may not be bad to for you to learn something fundamental. Then I will tell something, but that will come also if the time permits. Okay. So okay, so let's say I'll start with a simple complicated atom, let's say, to start with. So I will take, say, helium. This is 1s2, that is the electronic configuration. So how do you express the wave function of the helium atom? Wave function of the helium atom means it would be psi. It would be a function of the coordinates of the electron 1 and coordinates of the electron 2. But simultaneously, it's not that only one here, only two sitting over there, as we have done it over here. Okay, but still, we will have to bring in somehow electron-electron interactions, which is not there. So that we will show you when we will talk about the interaction, like Hartree-Fock theory and others, so how they are coming into the picture. So this one, it was first shown, let's say, by Slater, and we call this as the Slater determinant. So Slater has shown that you write some phi 1 as 1s into alpha, phi 2 as 1s into beta, because those two electrons, according to, say, Pauli principle, you cannot have both alpha, both beta, one alpha, one beta. So these are called spin orbitals. So these are orbitals multiplied by spin function. They are called spin orbitals. So it is 1 by root 2, this for the normalization, phi 1 1, phi 1 2, phi 2 1, phi 2 2. So these are the determinants. That means if you expand, what do you get? 1 by root 2, phi 1 1, phi 2 2 minus phi 2 1, phi 1 2. What was the logic given? That it's a probability function, so it must be multiplicative. So phi 1 in 1 and phi 2 in 2, or electron 2 is attached to phi 2 spin orbital, electron 1 is attached to phi 1 orbital. What is the joint probability? It is phi 1 1 into phi 2 2. But the thing is, electrons are indistinguishable. So equally valid is phi 2 1 and phi 1 2. So you take the linear combination of them. Now linear combination, it may be plus, it may be minus, it may have some constants, etc. But that he considered that you take minus. Actually, if you take minus sign there, then you get the determinant. Otherwise, you get something else. Okay. So you get all positive signs. So incidentally, these determinants you will get for fermions, which obey Fermi-Dirac statistics, like electron, proton, neutron, etc. Okay, but the determinants will not come for bosons, like photon, phonon, they will have all plus signs. Okay, because the wave function is symmetric with respect to binary permutation. So if you interchange the levels of the two particles, for fermions it will change the sign, but for bosons it will remain the same. So it is symmetric with respect to the corresponding operation. So in this case, you get the Slater determinant like this. So the very first thing you can check. So phi 1 means orbital has n, l and ml. So if it is 1s, what are n, l, ml values? Tell. 1, 0, 0. And ms is half. Here for phi 2, ms is minus half. That is the difference. Now, what is Pauli's exclusion principle? Pauli's exclusion principle is no two electrons can have all four quantum numbers same. Okay. So suppose if I want to say that electron 2 is also in phi 1, electron 1 is also in phi 1. So then you get all phi 1 1, phi 1 2, phi 1 1, phi 1 2. What would be the value of the determinant? If the determinant has same rows or same columns, determinant becomes 0. That means if the wave function is 0, the probability of getting the state is 0. So you can see, if you write it in the form of Slater determinant, Pauli exclusion principle is automatically taken care of. What about Pauli's antisymmetry principle? Just now I told that if you interchange the levels, the wave function must change its sign. So if I call 1 to 2 and 2 to 1, what will happen to this determinant? If I call, this is phi 1 2, phi 2 2, and this one phi 1 1, phi 1 1. You see, there is a change in the column. There is another property of the determinant. What is that? If you change either the two rows or two columns, the determinant changes its sign. So that is your Pauli antisymmetry principle. So both Pauli's exclusion principle and Pauli's antisymmetry principle, they are satisfied by this Slater determinant. If you have some n particle system, if you have some n particle system like psi 1, 2 up to n, actually 1 means 3 variables. Okay, so 1 by root n factorial phi 1 1, phi 1 2 up to phi 1 n, phi 2 1, phi 2 2 up to phi 2 n, and then phi n 1 up to phi n n. So for n electron problem, you will get n by n determinant, and again they will also obey your Pauli's exclusion principle as well as Pauli's antisymmetry principle. Okay, so you know how the wave function of many electron atom, so they are written. Okay, but still the problem is we are within the one electron picture, because we have written everything starting from the orbitals, and orbitals, they are solutions of one electron wave functions. That's why there is no electron-electron repulsion in their consideration. So it's a hypothetical case. We have to improve upon that, and that we will see how that can be done. Okay, so now I stop at this point.